going on the ice shelf of Greenland, the Inlandsis. It's one of the most extreme places on Earth. The cold is constant and there is no vegetation. The Inlandsis formed 250,000 years ago. It's 3 times bigger than France and as much as 3,000 meters thick. It's an immense ice desert which contains by itself 10% of all the fresh water on Earth. Accompanied by his assistant, Catherine Perrott, Professor Alain Coutet from the Museum of Natural History of Paris is here to study organisms capable of developing in this icy hell. To complete his mission, he is supported by a team of glacionauts, specialists in the exploration of subglacial caves. During 10 days, the members of the expedition will be completely on their own. In such an extreme environment, climatic conditions change rapidly. For protection, the laboratory has to be set up before nightfall.
Listen, nothing's broken. There's a light. That's great.
And well, everything's ready for work. But what a slog. It's hellish work to bring all that, a real exploit. But in order to study the extremophiles in their environment, this has to be done. With the snow, the rain and the humidity, it's awful. But to get living organisms and study them properly, you have to.
The team takes advantage of the first night on the ice to rest and enjoy a thrilling display of the aurora borealis. At the break of day, Alain Coutet and Catherine Perrott go in hunt of organisms which have managed to establish themselves in this hostile place. But first you have to know where to look.
Ah yes, look, a very nice cryoconite hole. It was always thought that on glaciers there was no life, and well, finally that's not true. There's life everywhere. However, it's in these tiny little holes, and the organisms that live here are microscopic. These holes are called cryoconite holes. That means cryo dust and conite cold.
These holes, which are in fact found all over the ice sheet, appear astonishingly cylindrical. But how can nature fashion such perfect shapes?
Cryoconite holes have been a mystery for years. Now we understand their creation better. In fact, they're caused by mineral and organic particles brought by the winds. These particles fall on the ice, and when the sun shines, they heat more quickly than the ice. They melt the ice around, and some will spin around on the ice, making a little cylindrical hole in the ice. They finish up by falling to the bottom, which is what makes that brown matter we can see in the bottom of all the holes.
These holes are in fact a true, if unstable, micro-ecosystem. They can evaporate beneath the sun or freeze at any moment of the day. In this precarious environment, somehow life has managed to develop.
And this substance, which we're bringing up with a syringe, is made up of microorganisms. We recover what we've sampled, and then the only way of seeing if there is in fact life is to look at it under the microscope.
Isolating organisms so small and in such a compact environment as the cryoconite is like looking for a needle in a haystack. It requires tools that are no bigger than a strand of hair. In the microscopic world, a single drop of water can contain a whole food chain. The cryoconites are made essentially of thousands of minerals and microalgae. These algae are the main producers of energy in this micro-ecosystem. By using photosynthesis, thanks to the sun, they make organic matter. This organic material is the favorite meal of rotifers. These strange creatures owe their name to two crowns of lashes which encircle their head and act like a wheel. They spin in opposing directions to bring nutritious particles to their mouths.
There aren't many predators here. There are the rotifers and the tardigrade. The tardigrade is the lord of nature here, the top of the food chain. Beyond that, there's nothing else living in this ecosystem.
The tardigrade, the super predator that rules here on the Greenland ice sheet, doesn't measure more than a millimeter.
There are so many cryoconites. There are lots of dark masses. You have to try to find this creature which is transparent, sometimes with a small brown mark, and sometimes it doesn't move, so you really must be vigilant and look at each little part of the preparation.
Tardigrades are amongst the smallest multicelled creatures. They're also known as water bears because of their strange way of moving. They don't swim, but use their impressive claws to hold onto fragments of vegetation, which gives them a shambling appearance. We find them everywhere on Earth, from the summits of the Himalayas to the depths of the ocean, and that's certainly because of their astonishing capacity to resist extreme temperatures.
It's a creature which can resist the cold by sleeping in the same way as a bear and waking when conditions become favorable once more. When a cryoconite hole freezes, it will be caught in the ice, and that won't kill it. When the ice melts, it wakes, and we think that that capacity to preserve its life is due to a substance, a sugar called trehalose, and we think it gets that sugar from the microscopic algae which can make it.
This sugar is diffused in the creature's body and acts like an antifreeze. It also protects the membranes of its cells against the attacks of the cold. Alain Coutet wants to observe in the field an even more astonishing adaptation of the tardigrade.
There doesn't look bad. Can you see the different layers of colours? And there are drain-offs. We can sample in that area there, but we have to find an easy place.
Well, listen, I think we should go a bit higher. No problem to do that. There's a good face. That should be perfect for it.
One of our objectives is to descend into these shafts to gain access to very old ice. You see, the ice is created by snow accumulation. Every year, 25 meters of snow compacts, makes layers and traps creatures and algae which are at the surface. By descending to the depths, we arrive at centuries which are distant from us, 4 centuries, 5 centuries, 6 centuries. In some layers, we may be able to bring tardigrades which are 5 centuries old out of the ice and see if they are capable of coming back to life. That's an experiment we can't make in the laboratory. There's a place where organisms have been trapped, and you can see elsewhere things trickling. We'll have a thorough look, take away the superficial part and recover the trapped organisms if possible.
These images, obtained by an electronic microscope, are exceptional. They show the astonishing capacity for adaptation of the tardigrade. When it is trapped in the ice, the tardigrade can put its vital functions on hold. The creature expels all the water from its body. It shrivels and limits its activity to the strict minimum. It can stay in this state for hundreds of years until conditions are once again favorable. Ice moulins are the only means of access to tardigrades trapped in ice that is over 5 centuries old. These impressive caverns, which can be over 100 meters deep, are carved by meltwater. When the temperature drops, the water freezes and the walls harden. The ice cave then becomes accessible. Glaciernaut Serge Aviot has already descended to 173 meters below the surface in one of these shafts. He holds the world record. When the temperature increases again, water streams down the sides of the shaft and they become unusable. That's why Serge Aviot watches the situation all the time. His descent to retrieve an ice core that is many centuries old is a real voyage in time.
What's the point of understanding this capacity of resisting death? It's a philosophical problem to start with because we're between life and death. If we can understand how the tardigrade resists these conditions of dehydration and apparent death, we could be able to apply it to man. It's a kind of dream. It would require analogous conditions, substances which could be injected, etc. What could keep us alive in face of extreme conditions? Of course, it's a bit of a dream, but it's the kind of things you have to study because it's a purely scientific question all the same.